right. ASTM, and you'll find this out a lot as you start reviewing ASTM standards, is that they will actually talk about how the data is supposed to be recorded. And so one of the things that they'll talk about, like with concrete cylinders, is what you're supposed to record the strength to. A lot of people just want to pop, load an area into their calculators or their computers, and they'll come up with 10 decimal places. Well, the ASTM says that's not needed, because what we should do is we should round all the cylinder strengths to the nearest 10 psi. All right. Going back, after now, again, this sort of lumps back to the ASTM, or excuse me, the ASTM and ACI, the building code, how we were talking about Chapter 5, but and we've already talked about the testing of a cylinder, but that's not the same as what the ACI is calling a test in Chapter 5, because in Chapter 5 they are actually talking about 2 cylinders and the average of 2 cylinders being tested as a quote unquote test. All right, so if we go back to whether cylinder strengths, concrete cylinder strengths, are going to be acceptable or not, now we go back to the very first thing we showed you. And really there's two parameters here. One is no test, and again, test is now 2 cylinders. No test is more than 500 psi below the design strength, and they call that design strength F prime C. And again, that would be like the strength that's established on a set of plans, or in a general notes, or in a project specification. Okay, so it would have to meet that, and it would also have to meet the requirement that the average of 3 consecutive tests, and again, there's that word test, which actually means 2 6x12 cylinders. Now, the 3 consecutive tests is greater than or equal to the desired design strength, F prime C. All right. So you might, think about, well, I've got a big project going on. I've got 6 hours of concrete pours that I'm making. What is acceptable as far as the number of tests is concerned? And in this case, the number of tests that you might do for concrete is really, as far as how on the maximum side of things, is really left up to the owner. That is, the owner can test as often as he or she likes. But what the ACI building code is going to require, as well as many building codes, is sort of minimum values. And so in this, again, quality control portion of the ACI building code, they will say that cylinders are to be made at least once a day, or at least every 150 cubic yards, or if you're doing a wall pour, at least 500 square feet of wall or slab. And it will talk about how the samples are to be taken from random trucks within the interval. Okay, so again, there's stipulations there as to how often cylinders are supposed to be taken in whatever you have. Steel is good in tension. Steel is good in compression. Steel is pretty good in shear. Steel, for most parts, pretty good in fatigue and bearing. But you get to something like concrete. Concrete's not very good in tension, not very good in shear, pretty good in compression, and things like wood. Wood is going to be a material that is very different tension versus compression versus shear. But wood's pretty good as far as fatigue goes. But so when we look at materials and we even say something like strength, like concrete has good strength, really what you're saying is concrete has pretty good compressive strength, because the other strengths in concrete are really not that great. So again, that's something, as we start paying attention in class this semester, that's something that you definitely want to keep in mind. What about weight? Weight's important property. And you might think, well, that's pretty easy. I mean, how important really is weight? Well, I mean, weight adds to the dead load of a structure. And you might say that, well, I know what a heavy material is. And my question to you would be, do you really know how heavy a material is? What about steel versus concrete? Which one is, and I'll say this with quotes, which one is heavier? Okay? A lot of people might say concrete is heavier because they look at a concrete building or they look at a concrete bridge and they just say that must be a heavy material. And you're right, sort of. Okay? If you look at density or the unit weight of steel and concrete, steel actually has a density of 490 pounds per cubic foot. Concrete, reinforced concrete, has a density that's typically taken as 150 pounds per cubic foot. So steel is more than 3 times denser than reinforced concrete. But a lot of people would say concrete's a heavier material, and I just told you that steel is more than 3 times denser than a reinforced concrete. How is that? Well, when concrete is made in a building frame, it typically takes on the shape of a square, a rectangle, a circle. It's a pretty bulky type of frame. I mean, the beams are rectangles, the columns are rectangles or circles, the slab is a rectangular slab. When you look at steel, typically we're looking at like rolled steel members, steel tubes, steel I-beams, angles. Well, steel, even though it's a denser material than concrete, it can be rolled into very specific shapes. So steel, even though it's more dense, a lot of people look at, and even when buildings are going up, they'll say, oh, that's a steel, must be, it's a pretty light building material. Well, by itself it's not light, but since we can roll it into certain shapes, it as a total structure, its dead load is probably a lot smaller than a comparable reinforced concrete structure. So anyway, when we talk about weight versus density, that's again something that you'll want to sort of bear in mind. What about stiffness? What about the ability to deform? The stiffness, how stiff is concrete? How stiff is steel? How stiff is wood? Stiffness is going to be not just a material property, but it's also going to be a property based on the geometric properties of the cross section. If you remember back to statics and strength of materials, we had some discussion about a property that was known as the moment of inertia. And if you remember back to statics and strength of materials, we talked about how moment of inertia actually related to a material's stiffness relative to bending. So again, a shape with a high moment of inertia, portion of geometric area, that's going to be stiffer. By the same token, if we compare steel to concrete, steel, based on its modulus of elasticity, is probably 10 times stiffer than concrete. So again, is there a trade-off there? So think about modulus of elasticity. The last one up here is brittleness versus ductility. Again, in a manufacturing realm, they might be able to accept the risk of having a more brittle material. In the civil engineering, construction management realm, architectural engineering realm, we would not typically want to accept materials that were more brittle. I mean, we like ductile materials. So again, trade-offs there that we have to be concerned. We could get into things like durability of the material. I mean, we have this idea that, hey, we design a building, we build a building, the building goes up, and possibly your idea is you forget about the building. Well, that's fine, but the owner's not going to forget about the building. The owner's going to want that building to last for a considerable amount of time. So how long is it going to last in a good state? So you have to think about corrosion. I mean, if you're in an environment that's a corrosive environment, I mean, is steel going to work? Is reinforced concrete going to work? Or is something going to work better? What's easier to put coatings on? What's easier to put certain technologies in place that maybe battle corrosion? So we have to think about that. Cracking, typically we don't think about steel cracking. If it does, we're in trouble. But concrete will crack typically. So again, does that, if that's in a corrosive environment, is that a bad thing? What about chemical attack? Steel versus concrete versus wood. What about freezing and thawing? Does that affect a material versus a different material? What about oxidation? What about abrasion resistance? These are all things that, again, we have to think about how our structure, how our design is actually being used. Because, again, you might have a client there that, is looking at a floor slab in a warehouse. And because of their traffic flow, they're really worried about abrasion of the slab, wearing it away. So, I mean, they might want, a hardened slab or something of that nature. Of course, the last one goes without saying, but what about fire resistance? I mean, steel is very susceptible to fires that are at an elevated temperature for some time. So what do we, how are we going to protect them? What kind of, what are we going to put them in something? Are we going to spray, something on them? How does concrete perform? How does wood perform? I mean, so these are all things that, again, might dictate you going a different way in a design, because not that it was a strength property, but it was something like fire, or it was something like corrosion. So these are all things that, again, you have to think about, and these are all things that, when you look at materials, that the ASTM and different standard writing organizations will write about. They will develop test methods relative to freeze-thaw resistance. They will talk about test methods relative to abrasion or corrosion or fire resistance. So, I mean, there are, things that, again, these things that are going to be addressed in those resources. And here's just a few more to end off the lecture with. What about resistance plastic flow? There's something that's called creep, which is a deformation under constant stress or prolonged stress. What about shrinkage? Again, with concrete, a material like concrete, shrinkage is an important concern. What about temperature susceptibility? We have our structures, our buildings that exist in predefined, or pretty much predefined temperature ranges. But, so steel, as it goes from minus 10 to 150 degrees, is it going to perform the same way? What about something like an asphalt pavement? Is that going to behave the same at minus 10 degrees versus 150 degrees? So, certain materials like asphalt might be very susceptible to temperature. Other ones like steel might not be. Okay, unless you're talking about fires and whatnot. But so that's just a few items to sort of get you thinking there.